I'm going to start from where we finished last time. So last time we actually understood that this simple antenna idea with an ADC architecture doesn't work very well for radio frequencies. And we covered a bunch of reasons for that. You may recall some of them. One of them, for example, was that the signal that you collect is so weak that you would have to actually get a 100 dB amplifier at the input at the RF frequency to actually get the signal at the right level. And as we discussed last time, this is a big no. This is a big difficulty. We can't do that. And so the natural question that comes here is, then why on earth do you actually choose to work with RF frequencies? Why don't you do something else? And this is a fair question because the fundamental principle is that the vast majority of signals, such as, for example, voice and video, essentially get encoded into bits today, and most of them will basically occupy just a few kilohertz up to maybe just a few megahertz of bandwidth. Our voice takes just a few kilohertz to transmit, if that, and video, even high definition video, takes just a few megahertz. So one might say, look, I have to transmit a signal that extends roughly from DC up to maybe a megahertz or two, or maybe 5 or 10, depending on the situation. Why are you asking me to go all the way to an RF band to work at gigahertz? Why do you basically take the spectrum that was here and now you're asking me to transmit it here? That's the fundamental question. So the answer to this question is by actually looking at what would have happened if we were to try to transmit the signal here, which we will call actually baseband signal, directly from an RF transmitter and receive it from an RF receiver. So the first thing that I have here is that there are some fundamental difficulties regarding antennas. Even if you have not taken an antennas course, what you probably remember from fundamental electromagnetics is that for a structure like this dipole antenna to efficiently radiate a signal or efficiently receive a signal, it needs to be somewhat large. And what we mean by somewhat large, I mean somewhat large compared to the wavelength. And the rule of thumb is that most antennas that basically transmit efficiently have to be somewhere between a quarter of a wavelength to half a wavelength. So lambda there is the wavelength. And you know, if you are pretty good in antenna design and you're willing to make a little bit of a compromise in terms of efficiency and in terms of bandwidth, maybe you can push this down to perhaps 0.1 wavelength. So less than that actually becomes really highly problematic, and there are niche applications where we do that, but let's just pick this as a rule of thumb. So if you actually do try to transmit at, let's say, 1 gigahertz, then you will find out that the length of your antenna has to be, let's say, 0.1 times the wavelength. And so the wavelength at 1 gigahertz would be the speed of light in free space divided by the frequency. So you'll find out that this is basically about 3 centimeters. So a 3 centimeter antenna, you know, it's not that big of a deal. We can all kind of visualize how we may be able to fit that into an actual system. But let's do the same calculation if you were to do this thing at baseband frequencies. So if we were to transmit, let's say, a 1 megahertz signal. If you actually do this calculation for 1 megahertz, you will find out that the answer here is an impressive 30 meters. Now that's becoming a little bit of an issue. Nobody really likes to carry a 30-meter antenna with them. And for voice, if you try to transmit 1 kilohertz, now we're talking. Basically, this guy becomes 30 kilometers. Does it mean that we transmit signals at 1 kilohertz? Yes, for unique applications we do. But for everyday applications, we would hate to do that. And so that's one of the most important reasons why baseband transmission, it simply doesn't happen. The antenna becomes highly impractical. So keep definitely that in mind as one of the reasons. Now, the other reason I want to give you is that, as I just mentioned, rarely we have signals that are at a single frequency, they usually occupy a bandwidth, right? So if you try to transmit, let's say, video that maybe occupies a bandwidth from 1 kilohertz to 1 megahertz, and you try to calculate the antenna size for that signal, when I used before the word wavelength, should I be using the wavelength at 1 kilohertz or at 1 megahertz or somewhere in the middle of the band? What is the right wavelength for this antenna? Well, the reality is that for signals that occupy a relatively wide bandwidth, as you can see here, there isn't really a resonant antenna like a dipole that will work well. You actually need a fairly wideband antenna to work well. And by a wideband antenna, I mean an antenna that can actually radiate well both the low frequency signal as well as the high frequency signal. And usually we'll measure the bandwidth, for example, by dividing the minimum frequency of the signal over the maximum frequency of the signal. So we'll say, for example, f max over f min. And in this case, the bandwidth is this extremely high number of 1,000 to 1. Or we will actually divide the maximum frequency of the signal minus the minimum frequency of the signal over the center frequency. And then we're going to talk about basically the fractional bandwidth of the antenna. Either way, whether we do f max over f min or the fractional bandwidth, you can see that if we were to actually transmit baseband, we would truly suffer in the sense that we would have to come up with antennas that are incredibly wideband. And that's a big challenge. It's not just a big design challenge, but it's a big implementation challenge. Wideband antennas like the ones I'm listing here, definitely, first of all, those are not 1,000 to 1. But even if you can make 1,000 to 1 antenna, you will actually end up with a fairly large structure. And so the second reason why we don't do direct baseband transmission is because if you do that, the f max over f min will actually be a very large number. Now compare this with a situation where you now don't do direct baseband transmission, but you actually center everything at 1 gigahertz. And now the bandwidth of your system is basically 1 megahertz minus 1 kilohertz, if that matters, divided by 1 gigahertz. And that's really, really small, right? So working with antennas essentially that have very small fractional bandwidth, you're practically looking at a spectrum that looks something like this, just practically a single frequency, which means now I can use small dipoles, I can use small resonant antennas, life is good, and the system works really well. So the second reason why we actually go for RF transmission and not baseband is because typically our fractional bandwidth would be much, much smaller than if we were to do direct baseband transmission. The other reason I wanted to also briefly mention is that we're not the only ones trying to transmit or receive. We don't create a cellular network, for example, as I'm showing here, for just one user or two users. We create them for a lot of users. For example, for GSM, you can handle 1,000 users at the same time. So somehow we have to find a way to share the channel. If everybody's transmitting baseband and all of our voices are roughly at the same bandwidth, then we're screwed. Basically, the person who wins is the person who screams the loudest. and that's not the way it would go. So for reasons of just sharing the channel, we have to basically find a way to give different frequencies to different applications. And there are many different ways we can do that. We're going to discuss later in the course very briefly frequency division multiple access techniques and time division multiple access techniques. But here I just want to highlight the need of sharing the channel. The other last reason I want to mention is that there is something called interference. As I just mentioned, you're not the only user, so you have to account for people who are transmitting close to you. And how do you reject that? So traditionally, an RF receiver, what they will do is that they will have the antenna here, that they will try to receive the signal. It will try to have some type of a filtering scheme, because what that filtering scheme will do is that it will basically try to take the signal of interest. There we go. It will take the signal of interest and it will basically attenuate annoying interfering signals that may be close to that. This is the role of that filtering scheme. And in the third 1 credit hour course, we're going to spend quite a bit of time understanding how do we actually design filters. Then there is this amplification. LNA stands for low noise amplifier. And then finally, you will have the rest of the receiver. Now, if these interferences are quite strong, then that technique works, but not too well. And to do justice here, if I were to do a real-life scenario, that frequency of interest would not simply be 2 times less than, let's say, interferer number 2, would not be 10 times less, would not even be 1,000 times less. The real life scenario is that this frequency of interest will be 50 to 60 dB less, sometimes 100 dB less from an interferer. That means 5, 6, 10 orders of magnitude below the interfering signal, and you still have to survive that. There are some more advanced techniques where essentially the interferer signal will basically have to be killed by additional notches that will come into the system, as I'm basically showing here. And these are some of the more advanced scenarios where that interferer is so strong and is so close to the signal that essentially a separate notch will have to come and take it out. Let me give you a real life scenario so you can appreciate the numbers we're talking about here. So let's say that you're trying to receive a GSM signal. Let's say that your GSM signal of interest is down at negative 99 dBms, which is roughly 0.1 picowatt. We discussed last time that it's with these sensitive receivers that we have to deal with. And the standard says that this GSM signal has to be received, so you have to be able to get to 0.1 picowatt in the presence of a blocking signal that is approximately negative 43 dBm. So there is a blocker, meaning an interferer, at a strength of 43 dBm, which is approximately 50 nanowatts, significantly stronger than the signal of interest. And this is only 600 kilohertz away from the signal of interest. Right? So imagine that this guy here is sitting at 1 gigahertz, for example. 600 kilohertz away, you have something that is basically many orders of magnitude stronger, and yet your receiver has to work. Now, to put that in perspective, this guy here is approximately 400,000 times stronger than the signal of interest, and it's sitting only 0.03% away from the main frequency. To put it more in perspective, imagine that you're looking at the bright sun when it's really summer and it's very bright, and the moon is right next to it. The moon actually is about 400,000 times less bright than the sun, the full moon, and your eyes can actually see the moon. That's what basically the GSM receiver can do. And in fact, the GSM receiver can attenuate a signal that is 10 billion times weaker, can actually detect a signal 10 billion times weaker than an interferer. In that case, though, the interferer has to be 20 megahertz away. So our receivers actually are so good that we can basically detect signals of interest in the presence of incredibly strong interferers that no other systems can do. Now, if you think a little bit about that, you might say, well, what's the big deal? Back in 1990, we created something called the Hubble telescope, which now has been able to find out faint stars that are 13 orders of magnitude weaker than our sun. So what's the big deal? Well, the big deal is that the Hubble telescope cost about $2.5 billion. There was only one of them in the world, and it took many years to build. A GSM receiver is practically available for free. It works in the middle of a city, not up there in the sky where everything is quiet. It works under any conditions, rain or shine, and we produce 1 billion of them per year. So that's the big difference. And so these are some of the reasons why basically choosing RF transmission is quite good.